Hi, my name is Kiran Baburaj. Welcome to Career Campus Pro YouTube channel. In this video, we will see how open addressing handles collision differently than chaining. The linear probing offers a space-efficient alternative that is widely used in many programming languages and databases. Let's begin by visualizing our HashMap structure. We are starting with an array of 7 buckets indexed from 0 to 6. Unlike chaining, in open addressing we store key value pairs directly in the array cells. Notice our size counter at 0. We will watch this grow as we add items to our map. Let's perform some put operations that will demonstrate how open addressing handles collision. First, let's add the key name with value John. We calculate the hash by summing the ASCII values and taking the modulus of the table size. For the name, it gives us the index 4, which is empty, perfect for our first insertion. Next, we will try main, an anagram of name that will hash to the exact same index. This is our first collision. With linear probing, we simply check the next available slot, the index 5, and place our entry there. And we are tracking both collision count and probe count. For mean, another anagram, we get another collision at the same index, and our linear probing algorithm moves forward again, and this time requiring 2 probes to find the next index at 6. The key age hashes to index 0, giving us a welcome break for the collisions. And further on, the key job and obj brings us back to the collision, demonstrating how the linear probing methodically finds the next available slot each time we encounter an occupied cell. We increment our position and try again, wrapping around to the beginning if needed. Next, when we try to insert the name with value Jane, our algorithm recognizes the existing key and updates its value instead of creating a new entry, a critical feature of any hash map. Now let's see how to retrieve the data when collisions have encountered. We search for the key name. We start as its original hash index and find it immediately. For main, we start at the index 4 and see that it contains a different key, and continue probing until we find the next index at 5. The search for mean demonstrates how linear probing follows the same path for the retrieval as it did for insertion, examining each position until it finds the target key or confirm it doesn't exist. Let's move on to the Python code implementation of open addressing using linear probing. In the HashMap class, first we define the constructor method, which initializes 3 key components: a size parameter that defaults to 10 slots, an empty array filled with non-values, a counter to track the number of items stored. Next, we implement a hash function. For string keys, we sum the ASCII values of each character and take the modulus of the table size to get the index. For other types of keys, we leverage Python's inbuilt hash function, again taking the moduli to ensure we stay within the array bounds. Now let's look at the add operation, which is where the linear probing comes into play. Before inserting, we first check if our table is full. If it is, we return false since we can't add more items. The core of our add method uses linear probing. First, we initially calculate the hash value for the key. Then we iterate through the possible positions using the formula hash value plus I mod size. If we find an empty slot, we store the key value pair and increment our count. If we encounter the same key, we simply update its value. In both cases, we return true to indicate the success. Next, the get operation also follows a similar pattern. We start at the initial hash position. We probe linearly through the table. Next, if we find an empty slot before finding our key, we know the key doesn't exist. If we find the key, we return the associated value, and we check all the position without finding the key, then we return none. Finally, for the delete operation, it's more complex due to the nature of open addressing. First, we search for the key using linear probing. Once found, we clear the slot and decrement our count. But simply removing an element could break the probe sequence for other elements. So we implement a rehashing step where we can check each subsequent position in the chain. For each non-empty slot, we temporarily remove the item, reinsert it using the add method. This ensures all items remain accessible even after the deletion. Let's summarize the key aspects of this implementation. The linear probing strategy offers simplicity and a good cache locality by checking consecutive slots during collisions. For performance, we can expect order of 1 average case for insertions and lookups, even though this can degrade to order of n in the worst case when many collisions occurs. And our special delete handling with rehashing maintains the integrity of probe chains, which is crucial for open addressing. And finally, we track the load factor by keeping the count of items versus the table size, which helps us to know when we need to rehash our table size. This implementation demonstrates an efficient approach to key value storage using open addressing collision resolution. Combination of good hash function and linear probing provides a balance in simplicity and performance for many applications. If you found this video helpful, please don't forget to like and subscribe. Happy coding. Thank you.